Hey, morning all. Over there in the R4DS world, we are going to continue here in studying the Bayes rules with chapter 9. At first, we literally see the words, we're going to build a simple linear regression model. But it looks like what we have in front of us is that we're going to understand the Bayesian approach to regression. And keep in mind, with all the concepts we have, we're going to interpret appropriate prior models. We're going to simulate the posterior model of the regression parameters and utilize simulation to build a posterior understanding between the response and the predictive variables, as well as build a posterior predictive model of Y. So things get fairly complex here. To the audience, I'm going to obviously go through the slides, and I once again thank the previous cohorts for really building this out. I added a couple things here or there. And as usual, if there's anything you have questions on or you want to discuss more, feel free to let me know. In the textbook, we are beginning Unit 3, and the previous cohorts had some very positive messaging here. We have come pretty far. We're chapters-wise about halfway through the book. I myself have been buying up these quote-unquote for babies books. They're very good for getting started. And this is how I view things right now. Unit 1, Unit 2, Unit 3, and there's just so much to see ahead of us. As you can see with the chapters coming up, we're looking at more sophisticated models, but in the Bayesian viewpoint. If you haven't done a lot of machine learning elsewhere, or it's been some time, just want to review some terminology here. We're going to treat capital Y as a random variable as our response variable. And we're going to have capital X's as our predictor variables. If the response variable Y is quantitative in nature, if we're trying to get a number out of this, it's called a regression problem. If we have a random or response variable Y that is categorical in nature, we call that a classification problem. Today, with the quantitative response, we're going to focus on building a regression model, and a lot that's going on in the background that I might not mention much today relies on normal distributions. So we call this the normal regression model. Our toy example today talks about bicycling in Washington, D.C., and we're going to try to understand the demand for it. In other studies about bicycling, because they're positive counts and usually thought of as whole numbers or integers, in other places you would consider a Poisson model, but as we want to become more flexible with how we approach the situation, we don't have the same mean or variance from day to day in talking about the data. For example, we have different seasons: winter, spring, summer, fall. And thus, folks who work with this, such as the authors, are going with a normal model where the likelihood is modeled with a normal distribution. The parameter for the mean is also going to be modeled as a normal distribution, being careful that the numbers there for its mean and its variance might be different. So we give them different symbols. As well as sigma might have a distribution as well, but we'll mention that in just a minute. The predictor variable will be the temperature in Fahrenheit. And the variable is described in the data as how people feel about the temperature, whether people feel that the weather is cold or warm, etc. Okay, so let's go about building the regression model. We have n pairs of data points between bike ridership, the response, and the temperature, which is the predictor. That is several xy pairs, or n of them. If we look at the data, which we will in graphs in just a bit, it suggests a positive linear relationship. That is situations where a straight line, a linear graph makes sense between the ridership and the temperature. And we have a hunch that the warmer it is, the more likely people are going to be using the bike sharing services. Instead of summarizing everything in the response variable with a global mean, we're going to actually calculate an average and each day that the data is available to us. So we're going to have several different averages. And then think of each average as coming from the linear relationship of beta plus beta 1x, where beta naught is the intercept and beta 1 is the slope. For beta naught, you could think about it as the bike ridership levels at 0 degrees Fahrenheit. Usually that interpretation is not all that important in regression inference. The intercept more or less helps you place the line on the data. However, it is nice to talk about the rate of change with beta 1. For every 1 unit increase in temperature, what would the change in ridership be? So we can now think of our likelihood with these ideas in mind. We are basing our observed counts with these parameters beta naught, beta 1, and sigma. Notice that the folks in the previous cohort didn't want to mention that we have independence from day to day in our assumptions. Also, the way we view sigma, the standard deviation, is variability around the local mean. Typo, that should have been sigma squared. But once again, assuming independence, assuming a linear relationship, and assuming that the variability will be also having a normal distribution. Thinking about the Bayesian viewpoint, let's ask ourselves, what are the parameters? And if we have to start with some prior models, how many do we need, or what exactly are we modeling at this point? I once again want to thank the previous cohorts for this neat HTML code where I could do a drop down on the results here if we click on the triangle. With our linear relationship in mind, we have these three parameters, beta naught, beta 1, and sigma. Once again, we're going to assume normal distributions for the beta parameters. Just be mindful that they themselves might have different means and different variances. Those are the hyperparameters of our situation. Now, for standard deviation, as we statistics teachers introduce this idea to our students, standard deviation is a non-negative quantity. This number cannot be negative. Using a normal distribution here might be a bit awkward. So folks such as the authors recommend an exponential distribution instead to reflect that non-negative quantity. So right now, we have our likelihood coming from these three parameters, normal distributed. In particular, beta naught and beta 1 are normal distributed, and the standard deviation has the exponential distribution. As with previous chapters, we want to think about the model building process. Whether or not our response variable is discrete or continuous, we want to have an appropriate model for the data. We think of the average of the response coming from the predictors with the linear relationship. We're going to be careful about identifying the unknown parameters. And as we see at the top of the screen, since we carefully considered the parameters, we got to now identify the appropriate priors for these situations, for these hyperparameters. The folks who work with this data quite a bit, who talk about this bicycling behavior, they would have some domain expertise and some knowledge about what we could use for our prior distributions. And thus, we should think about tuning the prior models to get ourselves into a good situation to then do our subsequent calculations with the likelihood and the posterior distribution. An average temperature day in Washington, D.C. is maybe between 65 and 70 degrees Fahrenheit. We have a rough range between 3,000 and 7,000 riders, which would put the mean around 5,000. If it's, I'm thinking, say, a uniform or normal distribution. A rough estimate of the slope at first, say in a frequentist approach, for every 1 degree increase outside, you add about 100 riders, but that slope itself is maybe give or take 20. And the daily ridership has a standard deviation of about 1,250 rides. There's also another careful inclusion of notation here. We work with centered data. Because it's easier to interpret. And the R package, rstan ARM, also uses that in mind. Okay. So right now, based on some of the domain expertise advice, our centered coefficient has this for its prior normal distribution, with a mean of 5,000 and a variance or a standard deviation of 1,000. For the beta 1, which is the slope, we're modeling with normal distribution, mean of 100, standard deviation of 40. Once again, sigma is modeled with an exponential distribution because standard deviation itself is non-negative. And if we go back through how we statistics teachers use the exponential distribution, we could equate the standard deviation, which is the reciprocal of the rate parameter, set that equal to 1,250, and we solve for the rate parameter here, literally 1 over 1,250. And that's how we get this number. The authors noted that at this point, we could do a simulation of the prior distribution, visualize these three distributions. But admittedly, we're going to focus on using the R packages for the overall process in just a bit. Okay, so let's see what we have so far. As usual, we want to update our prior. So we have, and thank you for the comment in the chat. One thing I probably should have done earlier is visualize the data. So that's what we're doing here now. On the horizontal, we have what the temperature feels like in degrees Fahrenheit. On the vertical, we have the number of bike share rides. This is coming from a paper by Fani T and Gamma. And I believe this is actually a subset of a classic data set from the machine learning repository over at UC Irvine. But nevertheless, what we see in front of us, scatter plot, positive correlation, positive slope on the regression model as we usually do in ggplot. But keep in mind, if we wanted to go through the process of the likelihood and the normalization to get the posterior distribution like we might have done in early chapters, there's a lot of information in front of us. And the normalization using the triple integrals, because 3 parameters, would be quite a lot. So we're going to instead model things with Markov chain Monte Carlo methods. And that is featured in the RStan ARM package, RStan ARM, where ARM is applied regression models. Let's look at the RStan ARM code. If we're going to build a generalized linear model, we are programmers like that the model formula syntax is the same that we learned maybe elsewhere for using LM, GLM from base R or other packages. Like usual, be sure to tell R where our data is coming from, what the name of the data frame is. We're assuming a normal distributed data. And as we had on the previous slides, our prior beta naught is model was a normal distribution with these parameters. Our prior distribution beta 1, the slope, has this normal distribution. And our prior sigma is modeled with this exponential distribution. As seen in previous chapters, what we're doing is building Markov chains for the sake of being able to do these calculations relatively quickly for just getting used to this. We'll build 4 chains. We're seeking chains that are 5,000 iterations long. However, because the MCMC process takes a while to quote unquote burn in or maybe start to converge in a sense, remember that we doubled that request. And then usual, we'll do a cute Bayes seed here. This all gets stored into our byte model. Now, in previous chapters, we actually used the rstand package. And what I like is that rstand arm, syntax-wise, code-wise, very easy to use. But just in case you're curious, if you did this process with the rstand package, we would define the model in a way that we might be familiar with from previous chapters, where we specify with this type of syntax what the data looks like, what the parameters look like, including the data type of the numbers, and the model distributions. We would then create a simulated model. The data itself, you have to be a little more specific, but the ideas for how much we want done for the MCMC are the same. Just keep in mind that rstand arm might be using a slightly different terminology than what we had in rstand. Remember that beta naught is the intercept. Even from here on, in the rest of this chapter, we might use the beta naught notation, even though it was centered as far as the inputs go. Beta 1, the slope, remember that's going to talk about the temp field variable. But otherwise, sigma stays at sigma. When we run this code, we'll get some results. But as we discussed in a previous chapter, might have been chapter 7, we need to check whether or not our simulation went well. How do we reassure ourselves that our calculations are reasonable? And remember that we have some metrics available to us. We could look at the sample size effect ratio. We could look at the R hat measurement. We could look at the trace plots. Remember that MCMC processes should look chaotic, but in an unorganized way. And we could look at the density plots of the chains. That is, if we're building approximations to the posterior distributions for each chain, their density should look pretty much the same, implying the same posterior distribution. Yeah, so let's start to see some of these results now. Being careful of the terminology, we're going to look at the bike model. We'll use the convenient tidy function from the brew mix package. Specifying the effects. Remember that the fixed variables are coming from the regression coefficients. The auxiliary variables is referring to sigma. If you study regression, this is analogous to how fixed is looking for the explained variation. The auxiliary is referring to the unexplained variation, or perhaps the noise in the data. And similar ideas to the coefficient of determination. For now, maybe seeking 80% confidence. We have our coefficients. This is an estimate for beta naught for the intercept. This is an estimate for beta 1, the slope. And this is an estimate for the assumed variance. And we have the confidence interval for each. Plugging in these estimates for beta naught and beta 1, we now have our posterior median relationship. Now, what bike model did, remember, bike model was built through this R-stand arm procedure. What bike model produced, we could view it with a quick conversion to a data frame, was actually 20,000 of possibilities of this linear relationship. So we could see that between the hyperparameters beta naught and beta 1, along with the auxiliary sigma parameter, we might get slightly different numbers. The 20,000 came from, we built Markov chains of 5,000 iterations each, and we built 4 of them, so 4 times 5,000. There are, once again, 20,000 of these relationships. Let's look at maybe 50 of them. The TidyBase package has a convenient wrapper to help us hone in on this idea for now. And if you do look close at the image, you can see that we have a little bit of variability in the diagonal line. We have some slightly different intercepts. We have some slightly different slopes. I'll fully admit, for this chapter, I did not actually run the simulations. Some of the folks who came before me noted that there were some complications, probably on the sheer runtime of this modeling process. When you get and do this for serious work, sometimes you let your computer run and do these calculations for a long time, for example, overnight. All right, so looking at what we have so far, thinking about the linear relationship in general, how do we feel about the implied positive slope? Do we have ample posterior evidence that there is a positive association between ridership and temperature? Keep in mind that in this image or in the above process, we drew 50 of those diagonal lines, of those regression model diagonal lines. And all of them, all 50 or sorry, let me say it this way. From the 20,000 observations that we could build this linear relationship on, in this sample of 50, all 50 had positive slopes. So that looks pretty convincing so far. We could build a credible interval for beta naught, and we find that the numbers for beta naught range from about 75 to 89. That is, the slopes are, again, not zero or not negative. And we could look at numerical evidence from the posterior probability. In a hypothesis test mindset, we briefly claim that the coefficient for beta 1, the slope, is 0. Well, in our 20,000 simulations, all 20,000 of them produced estimates for beta 1 that were greater than 0. So that seems like a lot of evidence against the null distribution. So let's reject the claim of 0 slope or 0 effect. With that in mind, let's move on towards posterior prediction to give ourselves something concrete to think about. Suppose that a weather report indicates that tomorrow will be a 75-degree day in Washington, D.C. What is our posterior guess for the number of riders that the capital bike share should anticipate? Okay, well, we could plug in the 75 into our posterior median relationship and get a number out of it. However, part of the reason why we're taking this Bayesian approach is to take into account sampling variability and the posterior variability. So let's carefully build a posterior predictive model. That takes both types of variability into account. We can approximate this with our 20,000 samples. on top of the bike model data frame from before, that is the 20,000 versions of these acquisitions for beta naught, beta 1, and sigma. We can now use our linear relationship, beta naught plus beta 1x, to get the individual estimates for mu. Remember that this was called mu sub I earlier. And then from there, once we have a mu and sigma, we could simulate the sampling variance. That is, there might still be some noise in the data, or said more practically, even if we had multiple 75-degree weather days, there could still be a different number of bicyclists who use this capital bike share program. Maybe we don't want to predict only one number, but also predict a range of numbers. That could be reasonable. So we predict multiple estimates for our response variable y. When we go through and get what was simulated with these ideas in mind, the folks in the previous cohorts did this quick extraction, looking at the 80% credible intervals for both mu and this y new variable. Mu, the credible interval goes from about 3,900 to about 4,100, whereas for y new, this goes from about 1,500 to about 6,500. That is, for mu, the credible interval is much smaller than it is for y new. Mu is, we could think of as the average ridership for a 75-degree day, whereas y new is for a Pacific day that happens to be 75 degrees. There's a lot of changing mindsets over here in Bayesian land. But for now, we could think of more accuracy in predicting for an average than for a unique point. A lot of curious ideas going on there. This has been a nice, long or deep dive into building a posterior distribution. If you do this quite often, the folks who made the RStan ARM package has this convenient wrapper code that will do all that all at once. That is, if we take our bike model, we could build, due to all the Bayesian thought processes, build a posterior distribution and predict what we have when we have a 75-degree weather day. Way back in chapter 4, balance and sequentiality, we briefly talked about sequentiality in the modeling process. Here, we could think about what would happen if we say only had the first 30 days of data. What if we had only the 60 days of data? And then what would happen if we had the entire data set? See if I could zoom in. Looking at these graphs, was the maybe focus on the light gray lines, all the possible linear regression lines that we're getting. When we have the first 30 days of data, especially because this is not necessarily a random sample. We have different seasons, winter, spring, summer, fall. When we have the first 30 days of data, we have some information, but you can see the light gray lines vary quite a bit. We have a lot of positive slopes and a lot of negative slopes. As we move on to the middle graph with 60 days of data, we seem to get more assurance that we have a positive relationship, a positive slope in the regression lines. And then the last graph, phase 3, is with the whole data set, especially including these warmer summer days, we get a more refined picture. If you are just diving into RStan and RStan arm, you or talk to myself really, I could simply use the default priors without having to really think about the domain expertise of it all. That is, if this capital bike share was my client and they wanted me to run these Bayesian regression models, well, maybe I don't necessarily have a sense of how many bicyclists are using the program right now. And maybe I want to leverage the Bayesian thoughts or concepts where we could start with a prior distribution, build a likelihood based on the data, and then especially with a reasonable amount of data points, we're going to be skewed towards a posterior distribution anyways. So perhaps the prior distribution does not matter as much. And we could take comfort that RStan arm could provide default prior distribution information. As usual, there's more in the textbook, but the defaults could be used to have prior distributions for beta naught, beta 1, and the variance or the standard deviation sigma. What would happen is that, as usual, your distributions would be updated. And then you could, once again, with these priors in mind, still do the process of going through the likelihood, dealing with the data, and getting a posterior distribution. That is, the priors were updated based on the original bikes data frame and model equation and some early calculations thereof. However, when you haphazardly use a assumption of what your prior distributions look like, you might have what are called weakly informative priors. That is, you start in a situation that might not be really representative of your data. So when we then build the regression models, the various diagonal lines that we see on the screen, if we don't have, or if we have weakly informative priors at the beginning, we could see compared to images like the one on the lower right here, we could see situations with a lot more variability in the lines that we get. Because at the beginning, we have a lot of variability with the intercept, the slope, and the standard deviation. And in fact, we might get situations with a lot of positive slopes and a lot of negative slopes. So that's another thing to consider. But nevertheless, when I'm just starting out with RStan ARM, I would try out the default priors and see how reliable the results are in the workflow. So to summarize the chapter, we have built a simple regression. We have built a simple Bayesian normal regression model with a quantitative response and predictor variables. Commentary. This feels like the first example of where Markov chain Monte Carlo simulation methods were really needed. We use simulated samples to summarize our posterior understanding of relationship between the response and the predictor. And we use those simulated samples, that is the many diagonal lines, for posterior prediction. The textbook authors literally have a section called "You Are Not Done Yet" to offer a couple of cautionary notes. We have learned just enough to be dangerous. That is, don't go around predicting things just yet if you're stopped here in the textbook. Because we want to, in the next chapter, spend more time evaluating the model and evaluating our assurance of using these Bayesian models. So that's going to be it for this week. Do folks in the audience have any more questions or comments?
No, not for me, thanks. Thanks very much.
Yes, thank you. And we'll see each other next week then.
Right, bye.
Bye.